the thing about the finite element method is we're in the business of solving partial differential equations, and partial differential equations that don't actually have any derivatives in them are kind of trivial and boring. I mean, you can do a Galerkin projection, but you can't actually solve a differential equation. So when we integrate the equations, they're going to have gradients in them. So that means it's not good enough to be able to differentiate things that are in the finite element space. We also have to, to be able to tabulate things that are in the finite element space, we also have to be able to tabulate the gradients of things that are in the finite element space. For reasons to do with how weak derivatives work that will turn up at some point in Colin's lectures, the good news is we only need to be able to do one derivative. This particular class of functions only has one weak derivative, so more than that would be what's known as a variational crime. So we've got to be able to do one derivative. So how's that going to work? So actually, the things that turn up in our expressions are functions in the finite element space, and that is to say that they are functions with respect to the basis functions. So they are weighted sums of the bases. So any function in the finite element space is the sum over the basis functions of a set of weights times the basis function values. So when I take the gradient of one of these things, well, this guy is a function of space. So in principle, it's got a gradient. This guy is a function of space. That guy is just a number. So it's just a scalar multiplying the derivative. And the derivative is a linear operator. So when I take the derivative of something which is multiplied by a scalar, I can take the scalar outside the derivative. So that's great. We never have to take derivatives of these guys. It does, the whole concept of taking the derivative of one of these guys doesn't matter. It doesn't make sense. So the only thing we have to be able to do is take the derivative of the basis functions. And that carries through one step further. Because what have we done? Well, we've expressed our basis functions as coefficients times the monomials. So the monomials are the polynomials that only have one term. So 1, x, y, xy, those are all monomials. And so the same argument applies at the next point, right? So our finite element basis functions are Vandermonde matrix, which is the expression of the monomial basis, times a set of coefficients. And it's the Vandermonde matrix which is spatially variable, not the coefficients. So we don't need to differentiate the coefficient matrix, we just have to differentiate the Vandermonde matrix. So that's good, because the Vandermonde matrix is made up of monomials, and I know how to differentiate monomials because I passed high school. So, or maybe, actually this is vector calculus, so you probably didn't see this till university, but you might have seen it in high school. And so what does that mean? Well, remember yesterday I told you to carefully ignore the optional grad argument to Vandermonde. So now the grad argument's coming back. So if grad is false, the Vandermonde function should do what you were asked to implement further above. And if grad is true, the Vandermonde matrix should evaluate the gradients. And what that means is, well, in 2 dimensions, so 1 dimension is going to be easier, but I will come back to that in a second. But in 2 dimensions, we have a function of x and y, its gradient is a 2 vector. And so when you take the gradient of the Vandermonde matrix, each entry in the Vandermonde matrix is replaced by a 2 vector, whose first entry is the gradient of that monomial with respect to x, and whose second entry is the gradient of that monomial with respect to y. So the whole Vandermonde matrix as a whole has become a 3 tensor. It's got rows, which are the points. It's got columns, which are which monomial we're currently dealing with, 1, x, y, whatever, and then it's got depth, and the depth is x and y. What you will probably find, so a lot of people have already noticed that when you make the plain van der Waals matrix, that actually it's easier to make the transpose of the van der Waals matrix than it is to make the van der Waals matrix, and that's fine. So you make the transpose of the van der Waals matrix, and then the very last thing you do is you put dot capital T on the end of the matrix, and it's transposed and you've got the right answer. Great way of doing that problem. You will probably likewise find that the convenient order for the dimensions to fall out when you build the van der Waals matrix here is not the right one. And that's also fine, so you can make it and transpose it, but now it's a generalized transpose because we've got 3 indices, and you can permute those 3 indices in 6 different ways. And so you can't just put dot T on the end because there isn't one transpose for a 3 matrix, there's 6 of them. But if you look at the transpose method on NumPy arrays, you'll discover that the transpose method takes a permutation as an argument. So that means you can build the gradient van der Waals matrix whichever way up you find most convenient, and then use a generalized transpose at the end to put it in the right order such that it satisfies the requirements and works. And the right order is in the question. So I realize you are all graduate students and telling you to read the question is patronizing in the extreme. However, this is true. So this tells you that the correct order is points, gradient, component, basis function. The reason for that is it makes it convenient to do matrix multiplies on it further down the line, right? So there's no inherent mathematical reason why these have to come in any order. You can always transpose everything and then do the right transpose multiply further down the line, but it turns out to be convenient to do it in this order, so that's the order we're going to do it in. There's 2 more things I'm going to say about this. The first one is that in 1D, the 1 vectors are not scalars trap applies here as well. So the gradient van der Waals matrix in 1D is still a rank 3 tensor, it's just that one of its dimensions only has extent 1. So you have to get that right, otherwise everything will fail and it won't work. And the other one is this hint here, so you should read that. So there are several natural ways to implement the van der Waals matrix. At least one of them involves doing 0 to the power of 0 quite a lot of times, which will introduce values into your matrix that are nan. So nan is a floating point value for not a number, because there is no sensible answer to 0 to the power 0. And it's fine to do the calculation like that, but the value you really wanted in those entries was 0. Like you've used a formulation which is slightly mathematically invalid and therefore puts the nans in there, but it's fine because you knew the answer was 0. And it turns out that doing that trick, so running algorithms which sometimes return nans, is a very widespread practice in scientific computing. And so NumPy provides a function for going through an array and turning all of the nans in that array into a specified number. So that is a way of doing that problem. It is not the only way of doing that problem. There are lots of ways.